This is Dr. Hawkins again, and welcome to what will probably be my final podcast for PLCs this semester. For new material, anyway. I reserve the right. I still may want to come on and do a review for a test or something like that. But this is my last one for new material, and I want to talk about Karnaugh maps with don't cares added to them. Now, here's what a don't care is. In some cases, we have some, like we've got a truth table, and let's say we've got 3 inputs, 0 to 7. So for some reason, we don't want to allow 7 with 1, 1, 1 input to ever occur. So we would make its output a don't care. I don't care if it's a 1 or a 0. So when I put that into the Karnaugh map, I can group it in with a group if I want to, if it makes things simpler, but I don't have to if I don't need it. So some texts use an X or an asterisk to represent their don't cares. I prefer the letter D because it stands for don't care. It's more clear what it's talking about there. So to illustrate this through a practical example, I want you to consider the 7-segment display that I'm showing on the left of your screen. And you can see I've got each segment not lettered A, B, C, D, E, F, and G. And we can use that by highlighting or lighting up only certain segments at a time. We can display each of the digits 0 through 9. For example, I'm showing the digits 0 and 1 at the bottom of the paragraph there and listing out the different segments that they use. You can see 0, for example, uses all these segments except for D. Now, I want to control this with a digital input. So I got to have, let's say, 3 push buttons. I want to go from 0 to 9, but 3 push buttons will only give me 0 to 7. So that's not enough. I have to use 4 inputs, which gives me combinations from 0 to 15. But since we only need the 0 through 9, we don't allow the 10 through 15 combinations. And so we're going to set their outputs to don't cares. Now, if you study this in another class, or that you can make this a hexadecimal thing and use the 7 segments to do A, B, C, D, E, and F also for 10 through 15. We're not going to do that here because I'm using this example to illustrate the way the don't cares work. So we're going to set 10 through 15 to don't care. Now, the next couple of pages, I just want to list out the rest of the numerals and list out which sections that they use. Here's 2, 3, 4, 5, and 6. Here are 7, 8, 9. Now, if you'll notice, if you gather up all of the A's, the little A's, all of the numbers where the section labeled little a is used, that turns out to be all of the digits except for 1 and 4. So here's a truth table for that. I've got my 4 inputs and I've got them laid out 0 to 15. And notice that number 1, number 1 here is a 0, and number 4 here is a 0, and the rest of them are all 1s. Now, if you did B, C, D, E, F, or G, it would be different, of course. And I do have a truth table for all of them that I'll show you later. But right now, let's just deal with A. Now, if I take this data and put in the Karnaugh map, here's what it looks like. and you see all the don't cares placed in there. Now those don't cares can be ones or they can be zeros. It don't matter. What does matter is I want to find the largest groupings that I can find, the least number of groupings, and the largest number of elements in each grouping to make the simplest min terms and the simplest Boolean algebra expression for the output A. Now, before we include the don't cares, I want to see what it would look like if all the don't cares were zeros and we couldn't include them. In our min terms. And you can see I've come up with 4 min terms, 1 group of 4 and 3 groups of 2. And I did not include any don't cares in this one. And I've color coded them, which min term comes from which grouping I circle. So you can take your time and go through those in whatever detail you want to. But this is the expression that I come up with. And you can see I've got 4 min terms. I've got 1 group of 2, that's the 4 here. And then 3 groups of 3, those are the 2. When I have 2 1s, that gives me 3 variables. When I have 4 1s grouped together, that gives me 2 variables. Now, having that for a comparison, let's go look at the well, let's do the same thing now, but this time let's include the don't cares in our groupings. And you can see I've got, instead of 3 groups of 2 like I had before, I've got 2 groups of 8. Those are going to give me single letters. That's my A and my C here. Again, I got them color coded, seeing which one goes to where. I've got 2 groups of 4. This is the BD and then the 4 corners. And I showed you that before. You can use the 4 corners as a group of 4. And that is B naught, D naught. And you notice that is significantly simpler than the expression we got the last example when we didn't include the don't care. Now, I do want to point out that we did include every single don't care in this example, but you do not have to. It just worked out that it was beneficial to get this group of 8 and that group of 8 and this group of 4 that we used all of it. But in other problems, there very well will be some don't cares that just really don't fit into the group, so you just exclude them. You don't have to circle them. You do have to get all the ones in, though. So we want large groups and the fewest number of groups that we can get, and that gives us the simplest expression we can have. Now, I've got one more slide I want to look at. I didn't want to write on that one, so I'll put this here. For homework, I'm assigning you the other 6 sections. And I do have a detailed assignment sheet that goes ahead and gives you the truth tables for all of those. It'll be a Word document, and I'll post it at the same time that I post this podcast. But let's go ahead and look at what the ladder diagram for this expression, the simpler one, would look like. I'm not going to try to draw that one. I mean, you could. There's no reason you couldn't. It's just more complicated, and I didn't want to fool with it. That's why we use the don't cares in the Karnaugh maps to get the simplest expression as possible and the simplest logic implementation possible in our ladder logic. So here is what that would look like as a ladder diagram. There's A or C or B and D, and these are closed contact, normally closed. It doesn't show up real good on this drawing, but you can see the slash. These are normally closed contacts That means these are the knots. That's B knot and D knot, and that gives me A. So what I'm going to do, and again, I've got a separate assignment sheet I'm going to post right after I post this podcast. I've already got it made out, and all I got to do is just put out an announcement. I'll give you the truth table. You do the Karnaugh maps, find the least complicated expression, using the don't cares when they benefit you, and ignoring them when they don't benefit you. You can use in the same Karnaugh map. You can use some and ignore some. And write out your logic expression and draw the ladder logic diagram. You can draw it by hand if you want to. I used uh, multisim. I just discovered multisim has ladder logic in it. I didn't know that until a couple of days ago. I just happened to run across it. You can download multisim yourself on a trial basis. Uh, and there is part of our license that lets students uh, have a license for it while you're in the class that uses it. I have been trying to get answers out of the multisim people since 2, 3, 4 weeks before the quarantine started, and they're not responding to my emails. So I got to find out what's going on with that. But we do have a site license at UWA that does include students. Anyway, you can draw it by hand, and when you complete the work, either scan it, you do it on paper, and then either scan it if you have access to a scanner. If you don't have access to a scanner, just take pictures with your phone and email them to me by the due date. I don't remember off the top of my head what the due date is, but it will be on the announcement that contains that assignment sheet. And again, if you have any questions, feel free to email me and I will respond as best I can. Have a safe quarantine. Hope everybody's doing well.